Hello everyone, welcome to the 4th semester physics lab. Today I am going to demonstrate the first experiment. This is basically an optics experiment, and this is an experiment where you need to determine the reflection and transmission coefficient of the mirror. So this is we need to find the reflection coefficient of this mirror and the transmission coefficient of this glass plate using this device known as the Lumiere-Brodin photometer. Okay, apparatus that are used into this experiment are the following. We require an optical bench. As you could see, actually this is a 2-meter long optical bench up to here. Okay, it has a centimeter scale placed on it. So this is a 200 centimeter or 2 meter long, and attached to it we have a vertical axis. Okay, so and you could see actually this vertical axis could slide in fact onto this optical bench. I will tell you why do we require that. We have these two sources of light and a photometer on the screen through which we could see actually what is happening. These has two holes in it through which the light passes from the two sources, which are kept opposite to each other, and of course these are the things whose transmission coefficient and the reflection coefficient need to be measured. Okay, so this is what we need to do is the following into this experiment. We need to in fact let's check actually what we have over here in this method. So here are the formula. Transmission coefficient is R2 prime by R2 whole square, and the reflection coefficient is A plus B upon R2 whole square. What is T? T is the transmission coefficient. R2 is the distance of the source of light, S2, without glass plate from the photometer. R is the distance of the source, S2, with glass plate from the photometer. R is the reflection coefficient, small r. A is the distance of the mirror from the photometer. B is the distance of the source, S2, from the mirror. Okay, so what basically we do? Obviously, you could see actually into this experiment we have these two setups. Here are the optical diagrams. In the first diagram, which is made for calculating the finding out the transmission coefficient, is following. This is the optical bench. We are placing the first source, then in between the photometer and the screen, and then the second source. Okay, and then what we need to do, we need to adjust so the light will pass through first source and the second source. We need to find a position of the screen where the source light from the two sources cancel each other. That is, we should find a dark spot into this screen, and this is where we need to record actually these readings. Okay, here it is. The readings are recorded into this table 1. So as you could see, position of S2 without glass plate, P2. Position of photometer, then R2 is what, capital? PH minus P2. Photometer reading minus P2, that is source 2 reading. Then after that what we will do, we will place the glass plate. Again, adjust actually the source and photometer, source 2 and photometer, and will photometer in such a way that the light cancel. That is the balancing position. Once again we find R2 prime, that is PH minus P2 prime. T is R2, so that way we will determine R2 prime and R2. Just take the ratio and square it. That is the transmission coefficient. So let me first do the first part. Okay, so here is my source. I am going to place my source this way. Make sure that this is on this side. Okay, so that we could note the reading over here. So I place the source, and in between I am placing the screen here, as you could see on the bench. Then the first source is placed here. Now what I will do, I will keep this source, say for example, at certain fixed distances. So for example, right now it is at 0. Okay, so this is the reading. Here is the setup. You could see this is the optical bench, first source, screen, and the second source. Now what I will do, make sure that the light, the source and this hole, the source and the hole, they are pointed towards each other so that the light passes them properly, and also we have the perfect optical plane so that things are moving smoothly. Now what we will do, we will switch on the light. So you could see actually the source 2, source 1 and the screen. Now if I see over here through this eyepiece, and if it is not a balancing position, I will see a bright spot, because you know that there will be an imbalance of light, and that is exactly is happening. So now what I will do, I will adjust it while putting my eye into it such that I receive a dark spot in between, okay, into this. So that means that I will receive the balancing position. It is still white, right, and now indeed I got actually a dark spot. So oh, I'm sorry, it has to be this way. Yes, it is a dark spot. So this is the situation. Now what I need to record, you could clearly check into the table 1. I need to record the position of S2. Position of S2 without glass plate. Obviously there is no glass plate. This is the position of S2. Let me read it. It is 152.5. Right, 152.3. So that is the reading you need to record over here. Then position of photometer pH. Here is the photometer pH. Position of photometer pH, that is 83. Okay, so these are the readings I need to record, and then I need to take the difference. Now you got this balancing position. Just don't touch any of these things. In fact, fix this S1 for now. And now what I will do, I will place this glass plate onto this source 2, and what I now need to do, I need again to repeat this experiment. That is, we need to use this photometer and the source 2, we need to adjust this in such a way that the light from the two sources again cancels, right? Again you need to record the reading S2, the reading of photometer, take the difference, that is going to be R2 prime. So you had R2, now you have R2 prime. R2 prime upon R2 whole square is the transmission coefficient. Okay, so let me do, actually I try to find adjust it and find the dark spot again. Okay, not here. Let me see. Well, I got it. Okay, so looks like I got. So I will again record this reading. Position of S2, position of photometer, which is essentially the same. In fact, I don't need to adjust. R2 is, this is something actually we need to adjust. So this will take the difference, will give us R2 prime, and this way you have got actually one set of reading. Now what we need to do, we need to adjust this by 10 centimeter. Okay, repeat the whole experiment again. That is, without the glass plate, adjust using S2, adjust S2 in such a way that you receive the dark spot into the eyepiece, record the reading of S2 and photometer, place the glass plate, again adjust the S2, record the reading of the photometer and the S2 prime, so that will be R2 prime, and that way you will again get another transmission coefficient value, right? Again keep adjusting it by changing it by 10 centimeter S1 and keep repeating actually this experiment. So this way you will take the 2-3 readings, take the average, that's going to be the average transmission coefficient. Okay, now in the next part, that's the reflection coefficient measurement. What we will do, as you could see, first half of the table is the same. That is, in fact, what you could do, I would suggest, well, that's going to be little bit tricky. But anyway, you could do actually that as well. Or so what you need to do basically, you need to follow the reading of this first part. They are going to be identical over here as well, because this is R2. Now you need to do the position of M mirror, and they take the difference of photometer minus mirror. That will give you B. So let me first make the arrangement. And so what you need to do now, place this S2 on this optical bench. Okay, again you could see actually there is a sliding scale over here. You could slide over the scale and okay, remove this. Okay, so this is the S2 which is now vertical. So how to make sure that the light again passes through hole? You know that if you place this mirror at 45 incident angle, so 45 incident plus 45, that will make the optical plane, right? Make the optical plane, place it at 45, the light will pass through it. Okay, light must pass through. So this is 45 plus 45, the light should pass through this. Let me put it down little bit. It is still moving here and there, as you could see, not good. Light should go down. Yes, not so good. As you could see, actually this light is moving here and here. It should go into this. So that means I need to lift actually this, either this thing or so basically we need to make the optical plane again such that the light passes through this. And once again what we will do, without disturbing the photometer, we will slide this whole arrangement in such a way that the balance is again obtained. We will record this reading of this S2 mirror and the photometer, and then reading, so that will be the third reading. So this is M, position of mirror. So here it is, this is the position of mirror, right? And then the second, so this is photometer minus mirror is A. Then distance of A2 from mirror is known as B over here. So this is the distance. Record this distance. What is the distance between the mirror and the source S2? So this is going to be A. Now the formula says R is equal to, that is the reflection coefficient is equal to A plus B upon R2. So this way you should be, whole square of course. So this way you should be able to obtain the reflection coefficient. Now once again, do this for 2 or 3 readings, 10 centimeter by sliding 10 centimeter towards the photometer. If you are starting from here towards one end, keep moving it by 10 centimeter each and record 3 readings. And this way you will again get 3 coefficients after balancing the things by moving the S2 and the mirror together. Okay, so of course you could in fact adjust this and adjust this whole thing. So this way you will have 3 readings, take the average, similarly take the average of T. That way you will be able to determine the value of T and R precisely for the glass plate as well as for the mirror. So this completes your experiment number 1. Okay.